We're now going to prove some results about the relationship between row-reduced echelon form and whether or not a matrix is invertible. And this is going to enable us actually to compute the inverse of an invertible matrix, which we'll do in the next video. So to get us started, we need a lemma about row-reduced echelon form. And this says that if you have a square matrix, so one which is n by n for some n, and that matrix is in row-reduced echelon form, then either it's the identity matrix or it's got a column that doesn't contain a leading entry. Before we think about the proof, let's think about the logical structure of what we're trying to prove. We have an OR statement which we want to prove. The first part of the OR statement is that x is the identity, so we might write that as I of x. So I of x is the property that the matrix X is the identity matrix. So we want to prove that I of x, or there exists a column with no leading entry. So we might write that as exists C, such that it's not the case that C contains a leading entry. So here C runs over the columns of our matrix, and L of C would be the property that that column contains a leading entry. So we want to show that either X is the identity or there exists a column which does not contain a leading entry. And you know some logical equivalences involving negation and there exists. So you should be able to remember there is an important logical equivalence which says that this is logically equivalent to, it's not the case that for all C, L of C. So there we have another OR statement where it's something or not something else. And there is a logical equivalence for statements like that as well. So again, it's an important one to remember, and the equivalent form is an implies statement. So the equivalent form is for all C, L of C implies I of x. Okay, what's that saying in our interpretation? It's saying if for every column has a leading entry, then x is the identity. Alright, now if you want to see a proof of this written out in full, you can find it in the notes for section 3.12. What I'd like to do on the other side here of this slide is just to give an indication about why this is true. So we'll just think about the n equals 3 case and try and convince ourselves or produce a kind of prototype argument that we could use in the general case. So let's say we've got n equals 3. Now since we're going to use the logical equivalence we established on the right, we're going to assume that every column has a leading entry and deduce that actually then our matrix must be the identity matrix. So if every column has a, I'm going to write LE as short for leading entry, well then there are 3 leading entries. So every row must have a leading entry because you've only got 1 leading entry per row at most. So we can ask, which column does the leading entry in row I appear in? So let's let Ci be the column, the number of the column. So this is a number. In which the row I leading entry appears. Okay, what can we say about C1 and C2 and C3? We have these numbers C1, C2 and C3. And C1 is the number of the column in which row 1 leading entry appears. And C2 is the number of the column in which the row 2 leading entry appears. And you know that in a row-reduced echelon form matrix, the row 2 leading entry must be to the right of the row 1 leading entry, which means C1 is less than C2. And similarly, C2 must be less than C3, again by the same row-reduced echelon form condition, which says that when you go down the matrix, the leading entries go right. So C1 is less than C2, it's less than C3. But C1 and C2 and C3 are the numbers 1, 2, and 3. They're all between 1 and 3. So the only way to have three numbers which are strictly increasing and which are all between 1 and 3 is to have C1 is 1, C2 is 2, C3 is 3. Okay, so let's draw this matrix now. What does this matrix X look like? X looks like this. It has the column in which the row 1 leading entry appears is column 1. So I've got a 1 here. And the column in which the row 2 leading entry appears is column 2. So I've got a 1 there and I've got a 1 there. Okay, so what about the other 6 entries in this matrix? Well, because my matrix is in row reduced echelon form, every entry in the column of a leading entry is 0. So every other entry in the column of a leading entry is 0. So I must have a zeros here and here. I must have zeros here and here. And I must have zeros here and here. So what I've got then is the identity. Okay, so we've shown that, at least in the 3x3 case, if you've got a square matrix which is in row reduced echelon form, and then either it is the identity or it's got a column which doesn't have a leading entry. So moving on, we're now ready to prove our main connection between invertibility and row reduced echelon form. So this says if you have a square matrix A, then A is invertible if and only if there exists a sequence of row operations taking A to the identity matrix. So let's look at how we might prove this. Let's begin by assuming that there are row operations which take A to the identity. So we'll call those row operations row 1, R1, R2, and so on. Let's say up to RK. Take A to the identity matrix of whatever appropriate size. So if you do R1, then you do R2, then you do R3, and so on, then eventually you do those things to the matrix A, then eventually you end up with the identity matrix. So you know that doing a row operation is equivalent to left multiplying by an elementary matrix. So let's let EI be the elementary matrix corresponding to the ith row operation here. So it's Ri of the identity. Now, since doing the row operation R1 is equivalent to left multiplying A by E1, and doing the row operation R2 is equivalent to left multiplying by E2, and so on, then if we take A, and we multiply on the left by E1, and then multiply by E2, and so on, and then lastly by EK, then the result will be the identity. So let's give a name to this big product here. Let's call this thing E. Okay, E times A is the identity. So that means A is invertible, doesn't it? Well, you might complain about this because the definition of invertibility was that a matrix A is invertible if there exists a matrix B such that B times A is the identity and A times B is the identity. So we haven't quite shown that A is invertible because we found a matrix such that when you multiply on the left you get the identity. But is it also true that A times E is equal to the identity? Well, that's not actually too hard to show now because we know that elementary matrices are invertible. And we also know that if you have a product of invertible matrices, then that's also invertible. So E is also invertible. we showed that a product of invertible matrices was invertible in theorem 3.5.3. Okay, so E is invertible. So what can I do now? Well, I can multiply my equation just here on the left by the inverse of E. So if I multiply on the left by e to the minus 1, I'd get A is equal to e to the minus 1. Let's have another go at that. So I'm multiplying my underlined equation there on the left by e to the minus 1 and getting this. And then I could multiply on the right by e to get A e equals I. All right, so that's just a cheap trick for showing that a matrix is invertible. It shows that if you want to show a square matrix is invertible, you actually only need to find a left inverse, because then it's automatic that that left inverse is also a right inverse by what we did here. Okay, so A is invertible, since we now just found a two-sided inverse for it. Alright, so we've done one direction. We've shown that if there is a sequence of row operations taking A to the identity, then A is invertible. So let's now do the other direction. So now suppose that there is no sequence of row operations taking A to the identity. So SEQ is short for sequence of no sequence of row ops taking A to the appropriately sized identity matrix. Well, what we know is that there is a sequence of row operations which take A to a row reduced echelon form matrix. So there is, because there always is, a sequence of row ops which takes the matrix A to a row reduced echelon form matrix R. Now R is a square row reduced echelon form matrix which is not the identity matrix. So what we just showed on the last slide is that R has a column with no leading entry. Okay, if R has a column with no leading entry, well then there are less than n leading entries, where n is the size of the matrix A. A is n by n. So there must be a row with no leading entry, because there is less than n leading entries. So LE is short for leading entry as usual. Okay, so R has a zero row. If there's a row with no leading entry, the only way that can happen is when there is a row which is the zero row. So by zero row, I mean a row which is all zeros. Okay, so this matrix R is not invertible. We showed that if you've got a matrix with a row of zeros, then it's not invertible. So theorem 3.5.2 shows that R is not invertible. Okay, so if we let E be the same matrix it was before, so the product of the elementary matrices associated to the row operations which took A to the identity, well, E times A is equal to R. So E is an invertible matrix because, for the same reason that we saw before, so it can't be that A was invertible, because if A was invertible, then the product E times A will be invertible. Okay, there we go. So a square matrix is invertible if and only if there is a sequence of row ops taking it to the identity matrix. And that is our row-reduced echelon form criterion for the invertibility of a matrix. And the nice thing is this is reasonably practical to actually check. If you've got a 4x4 or a 5x5 matrix, then you can, with not too much calculation, actually work out the row-reduced echelon form. Whereas perhaps some of you have already know about the determinantal criterion for a matrix to be invertible. You can compute the determinant of a matrix, and the matrix is invertible if and only if the determinant is non-zero. But nobody really wants to compute 4x4 or 5x5 determinants. You'll see this when you learn about determinants in the next, in Algebra 2, if you haven't already seen it. So this is a much more practical criterion that you can use for determining invertibility. Okay, finally, let's get a corollary out of this, which is that which is another criteria for a matrix to be invertible. So it says a square matrix is invertible if and only if the only solution to the matrix equation A times X is the zero vector is when X is the zero vector itself. So, proof, one direction is easy. If A is invertible, and if you've got any solution to that matrix equation, so let's say A times vector V is equal to the zero vector, then multiply both sides on the left by the inverse of A. What do you get? Well, on the left-hand side of our equation, we cancel the A out. It becomes the identity, so you just get V again. And on the right, you get A inverse times the zero vector, which is always the zero vector again. Okay, so we've shown the only solution, V, is the zero vector. So conversely, let's suppose that A is not invertible. Then let's let R be a matrix which is in row-reduced echelon form, which you can reach by doing row ops to A. So a row-reduced echelon form matrix obtained by doing row ops to A. So that's what people mean when they say let R be the row-reduced echelon form of A. They mean a row-reduced echelon form matrix which you can get by doing row ops to A. So R cannot be the identity by the previous theorem, the theorem we proved on the last slide. So R has a column with no leading entry. Okay, if there's a column with no leading entry, there is at least one fundamental solution to Rx equals 0. Right, if there is a column with no leading entry, then there is a free parameter in the solutions to that matrix equation. And if there's a free parameter, there is a fundamental solution, and fundamental solutions are not 0. But the solutions to Rx equals 0 are the same as the solutions to Ax equals 0, because when you do row operations, you don't change the solutions of your matrix equations. So Ax equals 0 and Rx equals 0 have the same solutions because R resulted by doing row operations to A. So this fundamental solution, which was not 0, is also a solution to Ax equals 0. So Ax equals 0 has a non-zero solution.